Hey everybody, and welcome to our next video in this equilibrium unit, which we are going to focus on the equilibrium constant K, which we've already been talking about, and relating that to the reaction quotient Q. So, as we've already seen, right, especially with that snowball activity that we did, at the very beginning of a reaction, you're not going to have conditions that are in what we call equilibrium, right? So if I have a whole bunch of reactants that are present, and if I have no products that are there, the reaction is not what we consider at equilibrium. And that's because they're just not the correct conditions. And we can compare mathematically, do we have a reaction that's at equilibrium? So if I'm given a bunch of concentration conditions, am I at equilibrium? Is that particular equilibrium constant equal to what I'm supposed to get? So we're going to use the equilibrium constant K, which is what we've already been talking about, and relating that to a new variable called Q. And Q is going to be not at equilibrium. We'll say not necessarily at equilibrium. So there's some conditions. We're given the condition of a reaction. We want to know, is this at equilibrium based on those particular conditions? So Q has the same exact expression as K. So in the last video, we were expressing K by looking at the equilibrium expressions based on the balanced chemical equation, and we were able to write that for them. Except the reactant and product concentrations or partial pressures are not necessarily at equilibrium. So here's a particular example here. So I have sulfur dioxide is reacting with oxygen gas, and I'm producing sulfur trioxide. In this particular equation, we're looking at concentration values, so it's Kc. Notice that the equilibrium constant is very large. It's well above 1. That means that I must have a very high concentration of products because that value is very high. So my value or my expression for the value of Kc would be equal to my concentration of SO3 raised to the second power over my concentration of SO2 raised to the second power times my concentration of O2 raised to the first power. But notice your concentrations must be at equilibrium in this case. Q has the exact same expression, except we don't really know if we are at equilibrium. So we're using the values that could be given to us. We're using a set of concentrations, plugging them into this value, into this expression, and seeing how does Q relate to K. So we'll say, how does Q relate to K? If Q is equal to K, that must mean that I am at equilibrium. Right, if I'm given a certain set of conditions, and if that equals the equilibrium constant, then I know that at that particular moment in time that that's at equilibrium. But sometimes they're not. And we can tell whether or not we have went past the equilibrium or if we have not yet reached the equilibrium by plugging in a set of concentrations, which is what we are going to do here. So, consider the following 3 experiments and determine if the reaction above is at equilibrium. If not, we'll state if the reaction favors the production of reactants or the production of products. So let's take a look at experiment 1 first. We're going to plug in all of these concentrations for experiment 1 into my equilibrium expression. But I don't know if this is at equilibrium or not. So we're going to figure it out. We know we'll be at equilibrium if my value of K is equal to 2700. Let's see if that's what we get. So we'll do Q is equal to my concentration of SO3, which is 0.7 squared, over 0.3 squared times 0.4. And when I do that, I get a value of 13.6 for Q. So notice how Q is much smaller than K, right? In this particular experiment, Q is not at the value of K just yet. So Q is much less than KC. Because of that, we know that this reaction must not be at equilibrium. I have not yet reached that equilibrium constant, right? So as a result, because I have not yet reached the equilibrium, I have far too many reactants that are still here, right? So I have too many reactants because my concentration of my products is not high enough, right? I need to produce more products in order to get the value of K to get even higher, to reach 12,700. So we know that this reaction favors the production of more products. In order to get Q to equal 12,700, I have to make sure that this concentration is significantly higher, my products. And to do that, it's going to produce more products. So experiment 1, we are not at equilibrium. In fact, the forward reaction is going to be favored. So we'll say forward is favored. Let's take a look at experiment 2. So I'm going to plug in all of these values in for this same exact expression. So I'll do Q is equal to concentration of 21.38. So we're actually increasing quite a bit here, as we could see. So our value for Q should be a lot higher. And I'm actually keeping my concentration of reactants the same. And when you solve for this, guess what? You actually get a value of 12,700, which guess what? This particular value is equal to our value for Kc. That means that these particular reaction conditions, when I have a concentration of sulfur trioxide at 21.38 and my reactant conditions are 0.3 and 0.4, that gives me a value of Q to be 12,700. This particular reaction is at equilibrium, okay? And that's because Q and K are equal to one another. So we'll say at equilibrium. Let's try experiment 3. So experiment 3, I'm going to plug all of these values in and do the same exact thing. So I get a value of 50. Notice how my product concentration is much higher now. So you could probably anticipate what's going to happen to my value of Q. So 50 over 0.3 squared times 0.4. And I get a value that's equal to 69,000. So holy moly, this value of Q is much larger than my value for Kc. So Q is higher than Kc. In this case, this means that my concentration of my products is way too high. So I said here that my concentration was too low. I needed to raise it in order to reach the equilibrium. Here, I actually have to lower this concentration in order to get it to reach equilibrium. So I'm going to say we're going to lower it to reach equilibrium. And here we have to raise it to reach equilibrium. Okay. So in this case, this numerator is far too high, which means that my final answer is going to be far too high. So in this case, because my concentration of products is far too high, I have to lower it. How do we get the concentration of my products to go down? The reaction is going to favors the formation of reactants. I got to make more reactants in order to reestablish an equilibrium. So in this case, the reverse reaction is favored. Reverse reaction favored. So if I'm given a set of conditions, right, whether that's going to be concentrations or whether that's going to be partial pressures, I can tell whether or not that reaction is at equilibrium by plugging in those numbers into the equilibrium expression and seeing, does that value for Q, which is not necessarily at equilibrium, does that match the value of K? If it does, it's at equilibrium. If it's too high, my value for Q, that means that it has to go ahead and make more reactants. If it's not high enough, it has to make more products. So this can tell us quite a bit of information here. And I actually outlined it up here as well. So when Q is less than your value for K, this doesn't have to be Kc. This could be just any value for K. So you could actually cross that off because we're working with, it could be Kp, it could be Keq, it could be Ksp. You're going to see a couple of different scenarios with K. So let's use this chart right here and do a sample problem 7 together. So we're given a bunch of reaction conditions, a bunch of concentrations, and we want to know, is this reaction at equilibrium? If it's not at equilibrium, is this particular reaction going to favor the production of products, or is it going to favor the production of reactants? First, let's go ahead and write an equilibrium expression. So it looks like my value for K is equal to, I am given concentrations here, so I'm going to use Kc. Concentration of ammonia squared over my concentration of nitrogen times my concentration of hydrogen cubed. So let's go ahead and plug these in right here. And it does tell me actually the equilibrium constant is, K is equal to 6.0 times 10 to the negative 2. If I consider that just right off the bat, which side of this reaction is favored based on that value of K? Because this value is so small, that must mean that I have to favor this side of the reaction. My concentration of my reactants is going to be very high, which then lowers the concentration, which then lowers the equilibrium constant. So right off the bat, at equilibrium, I have a higher concentration of reactants. Let's plug these numbers in and solve right here. So my value, and I'm going to set this equal to Q because I don't know if these are equilibrium conditions just yet. I have 1.0 times 10 to the negative third, and that's squared, over 1.0 times 10 to the negative fifth times 2.0 times 10 to the negative third, and that's cubed. And when I solve for that, I get a value of 1.25 times 10 to the seventh. Holy moly, this value for Q is huge. This value of Q is significantly bigger than the value of K. So Q is much, much bigger than the value for K. In this case, this means that my concentration of products is far too high, right? If I have too many products, this reaction has to try to produce more reactants in order to reestablish equilibrium. So in this case, we went past equilibrium. We produced too many products. Therefore, the reverse reaction is favored. This reaction has to reestablish equilibrium by producing more reactants. I have to raise the concentration of reactants in order to lower this value for Q. Let's see if these reaction conditions are at equilibrium. So I'm just going to plug these numbers in. Q is equal to, I have, let's see, 2.00 times 10 to the negative fourth squared over 1.5 times 10 to the negative fifth times 3.54 times 10 to the negative 1. If you solve for this correctly, you get 0.06. And guess what? That's equal to our value for K that was given to us in this particular example. So since Q is equal to K, these right here must be your equilibrium conditions. This particular reaction is at equilibrium. So let's see if this last reaction is at equilibrium. So again, I'm going to plug in all of these concentrations and solve. So Q is equal to, we have 1.0 times 10 to the negative fourth squared over, got a very high concentration of nitrogen here, 5 molar, times 1.0 times 10 to the negative 2 cubed. And I forgot my cubed up here too, actually. And when I solve for that, I get 0.0020. In this case, Q is too small. Q is less than K. So in this case, I have to try to increase my amount of products right here. I don't have enough products in this particular example. My concentration is too low. If this concentration is too low, that means that Q is too low, which is exactly what we're seeing here. So in this case, this is not at equilibrium. Not at equilibrium. In fact, the forward reaction is favored. I have to try to make more products in this case. I have to raise my concentration of products and lower my concentration of reactants in order to raise that ratio, to raise that value of Q, so it is in fact equal to K. So as you can see, given a whole bunch of reaction conditions, you can tell whether or not a reaction is at equilibrium by comparing it to the equilibrium constant, which is going to be given to you in a particular example. And that's what we did here. We'll get lots of practice with this in class. What I want to talk about now in this video as well is just properties of the equilibrium constant. So back here, right, we saw that the equilibrium constant for this reaction is 6 times 10 to the negative second. We saw up here that it was equal to 12,700. So using some simple math, we can actually manipulate these values for K. And that depends on whether or not we flip our reaction, whether or not we have to multiply our reaction by 2. So we're going to see here how this particular thing works. So K, of course, is going to be dependent on temperature. So a lot of times you are going to see that when you're given an equilibrium constant value, that a temperature is stated. And that's because your equilibrium constant can change with a change in temperature. You might remember in Chem 2 talking about endo and exothermic reactions. Depending on whether or not a reaction is endo or exothermic can affect the production of products. We're going to kind of circle back to that after equilibrium. I wanted to do that first, or I wanted to do this first, but I did want to reiterate that your equilibrium constant is in fact dependent on temperature. If a reaction is reversed, so let's say I take this reaction right here and I reverse it. So my ammonia is my reactants and my nitrogen and hydrogens are my products. In this case, your value of K is inverted. So I have a value of 1 over K. Okay, so when a reaction is reversed, I have a value of 1 over K. When stoichiometric coefficients of a reaction are multiplied by an integer, K is raised to the power of that integer. So let's say I take a reaction and I multiply it by 2. So you might remember talking about redox reactions when you had to take a reaction and multiply it by 2 to get the correct number of electrons on both sides. You're not going to multiply your equilibrium constant by 2. You're actually going to square it. So you're raising it to the power of that integer. When reactions are added together, as in Hess's law, we didn't talk about Hess's law yet, but we will, again, circle back to that. The K of the net reaction is the product of the values of K for all of the reactions. So I have to multiply them by one another. There's some mathematical reasons as to why it works the way it does, which I'm going to show you that in class. But for now, this is just a very quick crash course on how to determine or how to manipulate the equilibrium constant based on switching the reaction around a little bit. So let's take a look at sample problem 8, and then we'll be done with this video. So this is asking, calculate the equilibrium constant for the following reactions given the following information. So I have 2C is creating or is in equilibrium with A plus B, okay? If I notice, I have to try to see which ones of these reactions kind of fit with this, okay? And if I notice, it looks like this reaction is the best fit. So in fact, I have A and B are reactants here, and my A and B are products here. And my 2C is my product in this reaction, whereas in this top one, it's the reactant. So in this case, you don't even need to consider this second reaction. But it's asking us, how would that equilibrium constant be affected if I flip that reaction around? And if I flip the reaction, K is going to be inverted. We are going to take the inverse, so 1 over 4.39 times 10 to the negative third. And that particular value is going to give me my answer to that new equilibrium constant. And this makes sense because in this particular reaction, K is very small. So this must mean that I'm favoring this side of the reaction. I have a higher concentration of A plus B in this reaction. Whereas if I flip this around, I still have to favor A plus B. But in this reaction, A plus B are my products. So if my products are high, that must mean that my equilibrium constant must be high. So notice in this case, when your higher concentration is on the reactant side, I have a very low value for K. But when I flip them so they're on the product side, I have a very high value for K. So that's a mathematical reason as to why we take the 1 over the equilibrium constant to get a new constant for the reverse reaction. Let's take a look at this one right here. So I have A plus B is in equilibrium with D plus E. So if I consider this reaction, I have to do a little bit of canceling here, right? So it's almost like a net ionic equation type thing, and we call this Hess's law. So it looks like 2C is a product on one side and a reactant on another. So I can actually cancel those out and get A plus B is in equilibrium with D plus E. So I have to add these two reactions together in a sense. When I add two reactions together to get the new equilibrium constant, I have to multiply these by one another. So my value for K1 times my value for K2 is going to give me the new value of the total equilibrium expression. So I would take 4.39 times 10 to the negative third times 1.15 times 10 to the fourth. And that's going to give me a value of 50.5. So for this sum of the reaction, the equilibrium constant is going to be 50.5. Because this is a relatively large value, it's much greater than 1, we would have a much higher concentration of D plus E at equilibrium. Let's take a look at this one. This one's a doozy, but we could figure it out. So here's the reaction that I want to get to. Looks like here, holy moly, I got to have NaCl on my product side, and here it's on a reactant side. And I got to have N2 and O2 on the same side, and Cl2. So I got a lot of stuff to kind of cancel out here. Let's go ahead and we'll flip this reaction first around. So I have NO2Cl is in equilibrium with NOCl plus 1/2 O2. So I flipped this. If I flip it, remember, I got to take 1 over that equilibrium constant. So in this case, I'm going to take 1 over K2. I have to invert it, is what they call it. That gives me NOCl on my product side right here. So if we highlight this, right, NOCl is there and I have NOCl there. Notice though that I do need to add 2 of them, right? So I have 2 NOCLs. So I got to times this whole thing by 2. So what does that mean for this value? If I'm multiplying this whole entire reaction, if I'm doing it twice, I have to square that equilibrium constant. So I have to square the inverse of K2. So if I was to rewrite this over, I have 2NO2Cl is in equilibrium with 2 NOCl plus 1 O2. Okay. Now, this gets me to 2 NOCLs, but I actually have to get rid of O2 and I have to get rid of this guy right here. So I already used this equation. I don't have to worry about that guy. Let's focus on getting rid of this, right? So if I have this NO2Cl on one side, I have to have it on the product side to cancel it out. So I'm going to use this equation next. I have, and I'm going to rewrite it, NO2 plus 1/2 Cl2 is in equilibrium with NO2Cl. The way it's written right now, I only have 1 NO2Cl on the product side. So again, I have to multiply this whole thing by 2. What does that do to the equilibrium constant? I didn't flip it. All I did was I did the reaction twice. So if I did the reaction twice, I have to take K3 and I have to square it, okay, because I'm doing the reaction 2 times. Let's go ahead and do this math here and see what we have. So we're going to basically add these 2 equations together. Those 2 will cancel. And let's see what I'm left with. 2NO2 plus 1Cl2 is in equilibrium with 2NOCl plus an O2. So I'm a little bit closer to what I need. I do need to get rid of NO2s, and I have to also add a Cl. Nope, I have my Cl2 right there. So actually, let's take the highlighter and see what we have. So looks like I have that, which is right there. Okay. I have my Cl2, which is what I want. And looks like I need to use this N2O2, this equation right here. So let's see how we can manipulate that one to get the overall equilibrium constant. Just use that. Okay. So I have to get rid of NO2. Look at that. I have NO2 in my reactants here. I got to cancel it out by putting it in the products. So I'm going to rewrite this equation. 1/2 N2 plus O2 is in equilibrium with NO2. The only thing is I have 2 NO2s on this side. So I got to multiply this whole reaction by 2. What does that do to my value of K? My K1, I have to square this one as well. So let's go ahead and see if we get this final equation at this point. My 2 NO2s cancel. 2 O2s. I have 1 O2. Looks like I'll be left with just 1 O2. And that should actually solve it for me. So this would be 1 N2 plus 1 O2 plus a Cl2 is in equilibrium with 2 NOCl. Now that I got that whole entire thing settled out, let's figure out the equilibrium constant for all of these when we put them together. So it looks like I have to square K1. Then I have to do 1 over K2 and square that. And then I have to square K3, which I also have. So to get the new equilibrium constant, we'll say Kn, n is equal to the new equilibrium constant. I have to do K1 squared times 1 over K2 squared times K3 squared. Holy moly, that's a lot of work. But if you do it correctly, you will get 7 times 10 to the negative 24th. Very low value for K. which means this is heavily going to have a very high concentration of reactant. So this definitely favors the reactant side. This means that if I take these diatomic molecules, they're not going to come together very easily and form a lot of this. I'm going to have very little NOCl, and I'm going to have a heck of a lot of these guys right there. We are going to practice quite a bit of this in class, so please don't fret. I have not talked about Hess's law yet, but I think you can kind of get the general idea of it by canceling out what's the same on both sides, kind of like a net ionic equation. And we'll do more practice with that when I see you. Otherwise, if you have any other questions, please make sure you write them down. See me in class, whatever works for you. Otherwise, I will see you in the next video, which is all about using ice charts to determine equilibrium concentrations. Bye.